indicator that we can use to understand the dynamics. One of these is the local dimension around a certain point in phase space, and again locally in phase space we can define the persistence of the observation. So up to now, of course, this is very obscure, so let's try to understand what this means on simple examples. So this is the Lorentz attractor that you probably have seen at least once in your life. So it's a system of three equations, three variables x, y, z. And you see that if we start from an initial condition that is outside this compact object, we end up falling on the attractor. So in colors you have time. What you see is that once you are on the attractor, you can have very persistent dynamics around a certain point, this unstable fixed point of the dynamics, and then when you are in the chaotic region, the trajectory basically mix up, and also you can see that the colors mix up, meaning that we have recurrences of observation. So if blue is the beginning of the trajectory, then we have green. You see that at the end of the trajectory is red, we go again in the same region of the phase space. And this is the same as in the atmospheric dynamics. We observe recurrent patterns. So, for example, we observe storms, we observe blocking, we observe all this kind of phenomena that repeats. So, basically what we can do to understand how the dynamics is predictable in the neighbor of a certain point zeta is to introduce already the first concept, that is the concept of local dimension, that I want to introduce on the Lorentz attractor, but I will introduce taking as a dynamical system myself. And so if I'm a material point of this dynamical system, I can go in space, in the three-dimensional space. Let's assume that I'm not very good in jumping, which is a very good assumption. So my space becomes two-dimensional immediately, I lose 1 degree of freedom. And if I am locally in a very narrow corridor, I can just go back and forth. Probably I follow the direction of my head because I don't want to walk in it. So I will have only one possible degrees of freedom. The dimension locally in the corridor will be 1. I can go only in one direction. If I enter a big room, so it's still the same attractor, let's say, because I'm just changing the region of the phase space, but the room now I can go in two directions. So the dimension will be 2. But now let's imagine that I enter this room where the dimension is not 1 or 2 because there are rows and there are objects that I cannot basically avoid. I cannot walk on the table, otherwise the staff of the university will not be happy. So if I make this uncountable, I will have something between 1 and 2, and the dimension will be fractal. So this is also what happens in this kind of object, the Lorentz attractor. So we will see that in some region the dimension locally is higher and in some region is lower. So this is a different concept of the dimension of the attractor overall, which will be by definition the average of all the dimension of all the basically sphere that we can draw in the three-dimensional phase space around the compact object. So now the question is how we compute this local dimension, and this is the work I've done with starting from my PhD thesis some times ago with Valerio Lucarini, Sandro Vaienti, Freitas, Mike Todd. So mostly mathematicians and people that work on dynamical system theory, and there are also some statisticians, because for a very specific reason that you will see in a moment. So let's see very briefly how we can compute this local dimension. It's just to give you the flavor of what is the technique. I'm not going into the details of the theorem, but the idea is very simple. So we have a trajectory that now I consider discrete with a time m, okay? So I do m iteration of the trajectory starting from the point x, that is this guy. It can be a vector, can be a tensor, can be whatever you want. So after m iteration, I'm here, for example. So what I can construct the recurrences of the state zeta looking at the function of the distance between all the trajectory and the state zeta. Okay? Of course, if I want the recurrences, I have to look at the minima of this object, of the distances, with respect to the state I'm interested in. Clear so far? Okay, so now there is the trick, that is which observable we want to put here to have a good distribution of this guy.
So what is M?
M is time. So this is xm of x. So I will have a gm of zeta, because since I am on the tractor, the initial condition doesn't matter so much. What it will matter is just the point zeta. And I will use as weighting function minus the logarithm. Why? You know, for example, earthquake or the way ears and sound works. Well, this guy, earthquake, are measuring a logarithmic scale. So we have the magnitude, the Richter scale, for example, or the decibel. Okay. So for recurrences, Collet proved, and it comes also from a very old results by Poincaré, that when you want to go very close to the point zeta, this rate is exponential. So if we want to have a distribution that is basically easier to study, we apply this log factor. This is simply the reason. But it's not such a strict requirement. It's just to get rid of some parameter in the final estimation of the local dimension.
And the distance is just
The distance can be anything. It can be any metric you like if you have the full phase space. The results will be the same. I will come back to this question later when we will look at SLP fields. So now, for any chaotic system, this is the theorem by Freitas solved in 2008, so quite recent. Looking at the entrance in the ball around the point zeta is looking at the exceedances of G, because I put minus the log function, so the minima of the distances are now maxima of the minus logarithm, okay? So I will set the high threshold, and this threshold will correspond to my trajectory to enter in this point, okay? So once I have this, and the system is chaotic, I know the distribution of the entrance in the ball around the point zeta, that is just an exponential function. And this exponential function has two parameters. Now I renamed the G, the entrances in the ball or the exceedancy as Y, but you see you have two parameters which depend on zeta, and the scale parameter, the scale factor of this exponential function, is 1 over the local dimension. So the local dimension comes just from a fit of this object that is an exponential member of the generalized Pareto distribution. So why there are statisticians? Because basically I'm using some results, so sorry, here it should be GPD, from extreme value theory to study recurrences. Why? Because going close to a point in phase space is like observing some kind of extreme behavior, where I have a lot of space that I can explore, but I'm only interested in the minima. So the minima are basically studied by the extreme value theory. Is it clear, the idea?
Zeta is not necessarily an extreme.
No, zeta can be any point. Yeah, this is very... So this, of course, zeta can be any point. But the theory that we use is the theory of extreme value theory to get these results. So this is a sort of central limit theory for recurrences, where we use, because already the extreme value theory is a central limit theorem for extremes, and this is basically the way it's reformulated for recurrences. And that's why it's powerful, because we have the functional form of the distribution, so we can get dynamical estimates of the dimension just with the fit.
Yeah, perhaps, I mean, it helps to understand why you treat them as extremes if one thinks that Q, this threshold one imposes, can be a very high percentile of your distribution of distances.
Yeah, because imagine that Q is large, you will sample a large part of the attractor, but if you want the local dimension, you have to go very close to the point zeta. So now,
what are the hypotheses of this?
just system must be chaotic.
So I think if you have a diffusion, for instance,
Mhm.
and some chaotic system plus a weak one.
Yeah, this works anyway. So if you have
It
noise,
works anyway, but the result is trivial basically. You are looking at
it depends on the level of the noise.
you are looking at just the local distribution.
Yeah, then it should go. It should fit the phase. It should be the dimension of the phase.
So what you measure is looking at the density at the point.
Yeah,
and the
exactly.
variation.
Yeah.
So in my limited understanding of GPD, I think in terms of location, shape, and scale, so is sigma like the shape?
No, sigma is the scale. The
Scale.
shape is 0 because we get the exponential member, and in fact this is how we understand if we have converged to the right distribution. We fit a GPD, and then we do a statistical test to assess if we have the right member of the GPD, and that's why again we can trust the results because we know the functional form that we have to get at the end. Another way to so this will be very useful when we are in high-dimensional dynamical system because we don't know what is the dimension. So the reference for
So what is the relation between the local dimension and the dimension of
it's the dimension of the tractor is the average of all the points Z. I will show you for the Lorentz. So this is basically the reference for the all the theorems that prove that, and there are also the case for a stochastic dynamical system that Freddy was mentioning. It's inside this. There is an entire chapter for stochastic dynamical systems because the things are less trivial than what when the noise is very low, you can still have some effect of the deterministic dynamics, and there are also let's say the noise just not induce just chaos, but you can induce also periodic behavior. There are special systems where you add noise and then you get something that is more ordered than the system of the bunch. So this is but in general it depends what you say, Freddy, of course. So in the Lorentz attractor, to answer the question of Freddy again, if we look at the distribution of the local dimension, we see already that we have some interesting structure. So the extremal point of the wings are high dimensional. So you see that these kind of extremes are traced by the dimension, and there is also an interesting region here that is near the, and also here, but I don't have for this trajectory enough point. That basically it's low dimensional because I'm in an unstable fixed point, so I'm trapped to follow a kind of very low dimensional dynamics. And there is this very nice region I wasn't aware of, but that I discovered doing this analysis, that is in between the unstable fixed point and the chaotic, let's say, dynamics of the wings. Here, you can choose if you go back to the unstable fixed point or you go to the chaotic loops on the attractor. So there you have an increase of the degrees of freedom because you can go in the two kinds of dynamics. So it's nice that you can trace this. And the dimension of the attractor that from the classical estimates, Grasberger and Co. is 2.06 is exactly the average of this guy. What is interesting?
I don't understand why it is below this part that you just mentioned, because you said that it is in the last part it was completely blue, so very persistent. So here,
This is the persistent point.
yeah, but in the plot before it was completely larger.
Yeah, but in that case, that was a specific trajectory in which you spiral, and the option is you go close to the point. And there are very few directions that I visualize. But what happens in general when you are here is that you can go to the chaotic attractor, or you can be trapped. In that case, you were trapped, and you were trapped for a long time.
It was just one example of
It was one very short trajectory, but this is not that long either. It's 60,000 points. Whereas for the classical estimates with the box counting technique, you need millions of points to get the same kind of uncertainty on the results. So this part of using the extreme value theory, this central limit theorem for recurrences, somehow gives you faster convergence to the results if you are interested on the average.
So why does the dimension seem to go to 3 close to the boundary, 7 boundary?
Okay, here
It seems it's functional.
here it's but also there when you are pulled out of the attractor, what you see, you don't see the attractor anymore, so you see kind of a three-dimensional phase space, and then probably you will go back with the attractor. But
So it's a sampling problem.
it's not. I won't say that it's a sampling problem. Yeah,
The
maybe.
dimension should be zero.
But no, why should it be zero?
So you say that you are going out from the attractor.
But out of the attractor, you see the three-dimensional phase space, so the dimension
Out
should
of
be
the
three.
field, you are not there.
Huh?
You are not out of the attractor.
Yeah, you are not on the attractor, but when you this is there is a study from Polyglot that say when you have a trajectory that goes out from the attractor, you have two cases. Either the dimension is higher than the dimension of the attractor, or the dimension can be also lower. So for the Lorentz attractor, I didn't see this study, but because this study, the theoretical studies are for one-dimensional or two-dimensional maps. But it depends on the trajectory you follow. For me, my intuition is that you see a three-dimensional phase space, and then for an instant or for a second, you can go here and you just see this, and then you go back to the attractor.
I think that my interpretation is that if you are out on the outside of the wings, then you have equal chance of remaining on the same wing in the next rotation or jumping to the other, because you have somehow a faster speed.
Yeah.
So you could be ejected to the next wing, to the other wing rather easily, and this is what happens when you are at the center close to the stable point,
Yeah, I get it for the central point because that's where you're going in different directions. But on the wing, that's the most stable part. That's really
well,
wide.
that's the center of the wings, but the outside, you get speed and then you.
The outside of the wings is where you're most stable, right? Because you're just going around, and then when you get to the middle, that's where
You're going around, but you're going
And
so
there's
fast.
a local.
But here the speed increases somehow.
Yeah, you have a very low persistence when you're on the rig there.
Yeah, but this is a dimension, right? So this is just a local dimension. So when you're going there, you're just going in a straight line. There's no chance you're going to go in any different direction, right?
Gabriele, I'm afraid I will finish at night. Because, okay, so the way to check if it's a sampling problem would be to look at
The
the
other question is,
convergence.
how can you get less than one? Because you have to go in a straight line.
But the system doesn't, well, you have dimension, if you take the counter set, the dimension is 0.6 something, so you have a dimension lower than 1. If you do the iterating function system, when you just,
So if it's a fixed
if
point,
the map
it's-
is
it's-
contracting,
Because the objective fixed point is 0.
yeah, if it's of course, if it's an attractive fixed point without any probability of escaping, you can go to 0. Yeah.
Can I just ask a question about the statistical part? So,
Yeah.
in the extreme value theory, and what it says is, you know, if something converges, then it will converge the GPD, but it doesn't guarantee it converges. There's lots of distributions that don't converge to GPD.
Yeah.
So, how do you deal with that? How do you
So
know?
this is the theorem for the fact that I'm introducing chaotic systems somehow gives me already the distributional function for the recurrences that is exponential. So when I wait with minus the logarithm, I have that an exponential of minus the logarithm goes, since the tail is exponential, to the members. Of course, if I understand your question, we have also used it the other way around to detect when the system is not chaotic. Then we don't have convergence, because if the system is periodic, we go around the same point over and over. So what we will have, it will be a Dirac delta, and it will not converge to a member of generalized Pareto distribution. So we can use the results the other way around to detect when the system is not chaotic.
I mean, I would have thought there would be chaotic systems that wouldn't converge. I mean, in statistics.
Instead, no, because when the system is chaotic, somehow we recover the independence that we need for the generalized Pareto distribution after the decorrelation time is gone.
Before the mix in the hypothesis.
Yeah, this is the hypotheses are in Ledbetter book, and are D1 and D2 hypotheses on the decay of correlation. You need at least that more than a power law of decay to obtain these results.
I mean, there are stochastic systems,
Yeah.
purely stochastic, and which have no autocorrelation and never converge to GPD.
Yeah, but the other thing is that you need to have an attractor. You cannot go to infinite as you like. So you need somehow to be on a compact set. And this gives you basically, again, another help to the conversion. But it's not, what is the difference here is that we are looking locally with respect to a point. It's a statistics of the distance. It's not a statistics of the variable itself of the system. So there is a trick. But the important point is that there is asymptotic independence that is given by the decorrelation of the counting that we have in the counting, or the sensitivity to initial conditions. Okay. So another thing that we can measure is the persistence. That is basically how long when we enter in the ball, we are stuck in the ball. So if this happens, of course it will be some quantity that depends on the delta t used, if we have a continuous time system, because this will be delta t. Okay, so in this case, for example, we have one iteration, two iteration in the ball, in this case just one. So we will average out all this residence time, and then we will get the inverse. So 1 over this average residence time, and we will get an inverse persistent index. And again, for the Lorentz attractor, and here we see what Pascal was saying before, the extreme part of the wings in this region, especially also in this region, are the place where you go faster, because this indicator is close to 1. Instead, in the unstable fixed point, you are trapped. And you see also that here we have another unstable fixed point, that is the origin, where you slightly slow down, and then you basically go back in the loop. So this is some of this, the persistence is kind of a speed in phase space. Is it clear how we compute this? No. Okay, so I'll do it very fast here. So imagine that we are on the Lorentz attractor and we do this trajectory. Then I fix this point zeta, okay? Now I compute all the distances from zeta and the trajectory. And I look at the minimum distances, okay? So I'm away from the attractor, then I go here, then I go away, then I go here, then I go away, then I go here, and so on. So this is a cluster. So I'm staying close to the point for, let's say, 5 delta t. This is 4 delta t, this is 3 delta t, for example, okay? So the theta index will be 1 over the mean persistent times, so it will be 1 over 4 delta t. Okay, so this is between 0 and 1. With the whiteboard is always faster than with a slide. I don't know why. So the higher, so the closer to 1, the faster; the closer to 0, the slower. Okay, so again, this is for the Lorentz attractor. And now the things that I did with those guys here, so Gabriele, Pascal, Carmen, and Davide, is the application to basically the sea level pressure fields. Because in everything I told you, there is it is never mentioned. So the only hypothesis is the system is chaotic. Okay, so I fixed as a problem this one. So I consider all the maps in the answer pre-analysis from 1948 to 2015 or 2017 as my trajectory x of t, and then each maps will be alternatively my state zeta, from which I measure basically the local dimension and the persistence. Is it clear, the procedure? Yes. So I cannot represent now the dimension and the persistence on the attractor because I don't have it. It's not the Lorentz attractor anymore. What I can do is a scatter plot of the properties, so the dimension versus the persistence. I don't know if you can see it well. So you see that each point on this graph will be 1 day.
But so here you make a big jump. I mean, you need to define distance between that.
Yeah, the distance is Euclidean distance point to point. X, yeah,
You mean at the scale of itself?
yeah.
So the distance will depend much on the resolution.
No.
Actually, yeah, who's going to say no?
In fact,
That's just extraordinary thing.
it doesn't depend either on the database, either on the resolution, because we tried with the ERA 1979-2015, we coarse grained the ERA to 1.5 degrees, then we tried the NCEP that is at 2.5 degrees, and we coarse grained up to 10 degrees of latitude, which means that we have few points. And the dimension is, the estimate is stable. We did it also on Cordex. I tried also on Cordex, where the dimension here, basically the grid is 1000 points. We do latitude by longitude. Cordex is 100,000 points. So, and we get the same estimates. So, what is actually measuring is the number of degrees of freedom that are in the field. Since the sea level pressure field is a very large scale field, we get good estimates up to 10. And also, for different periods, we also tried from 8050 to 2200, so to have statistics that is almost an order of magnitude larger than this, because this is only 30 years, so from 30 to 300 years, and still the dimension is still stable on the same value. So we did this study. Another thing that can be interesting to mention is that since our, like in the Lorentz attractor, there are quasi-periodic behavior when we switch from one wings to the other, we also have seasonality in the atmosphere, and we don't need to remove it a priori because we are only looking at recurrences. So we will observe recurrences in the same season or in the symmetric season in spring and autumn. And what we see is that we get a seasonality in the dimension if we look at the time series. Okay? So what is interesting is that the spikes occur mostly in winter. We will look at the extremes to see what are these spikes that we observe in this indicator. If I answer your question, Freddy.
Maybe.
Okay.
I think we should discuss.
Next time we are in Paris, because I have to leave at 10. So.
Because there are two different things. One thing is that you compare the data you have.
Yeah.
One thing is to use a model with different resolution.
Yeah. So, but this is a different model. And this is the ghost grain of the model. And then we will have the 27 model of the signifier ensemble. Plus the other things is maybe the distances that we use. If we change distances, here we don't have the full space because I don't use temperature or precipitation. So it will change the numerical value of this guy, but the extremes, for example, if we use correlation, or the correlation between this time series and the one that I obtain using another matrix would be roughly 0.9, which are different metrics, and the results are kind of stable. So what we shouldn't really trust probably here is the numerical value, except to say that is a very low dimensional value with respect to the dimension of the phase space if we consider it as the number of grid points. No, I'm going in the wrong direction. So now I will comment these that are the extremes of these indicators. So one thing that we wanted to look at with Pascal and Gabriele was if the extremes of the indicators, so the minima of theta that corresponds to the highest persistence, the maximum of theta that corresponds to the lower persistence, the minimum of the dimension and the maximum of the dimension are just maps like these that can be any situation, or they actually have some kind of shape that we can recognize. And we try to do this zoology of extremes, and we start, for example, from this guy, that is the low dimension. You see that these are anomalies when we subtract the seasonal cycle. And we see this NAO++ pattern, because these are very strong anomalies. How can we be sure that we are actually averaging situations that are similar and there is not just few guys that bring it? In fact, if we look at if we require that at least 2/3 of the situation have the same sign anomalies, we get these lines that actually guarantees that here there is an anticyclone and here there is a cyclonic anomaly. If we look at this guy,
are you averaging all the points that
yeah,
lie in
yes,
this?
yeah, that lies beyond these quantiles. Of course, we move the quantiles to check that these maps remain the same. If we move to the right, we have the same kind of pattern, but the anomaly is reduced when we go towards the center until when we have a non-extremal behavior anymore, they somehow disappear. So this guy corresponds to a blocked pattern, and this is the higher dimension. This guy that is the less persistent one is an Atlantic region. This guy is a NAO minus. So surprisingly, we find somehow the weather regimes, but extremes here because the anomalies are very strong, as extremes of the dynamical indicators that we have defined. So another thing that we can say is that, in fact, the NAO plus pattern is the most predictable one. Why? Because if we imagine it's just a zonal flow that is like a very zonal flow, and in this case the flow can just go basically to the east, so we have a very strong jet, so it's very predictable to know what the flow will look in the sequel will be. Again, a zonal flow, maybe less strong, but it will be still zonal. Instead, when we are in blocking, we can go very quickly to a zonal state because this is very unstable, and we can persist in the blocking. So the system has options, and these options are higher dimensional. Okay? So
Sorry, I'm a synoptician.
yeah,
If the blocking is established, it's actually quite stable.
yeah, but you don't know when you will go out from the blocking.
No, we
This-
don't. But
And this
as
makes the
long,
things.
but once it is established, it's much more stable than a positive NIO.
But it's more stable in the sense of the weather pattern. But here we are looking closely in phase space, so it's not. It's how much the map resemble each other from one day to another, and it's more linked to the possibility that is the flow when it's there. So when the zonal flow, maybe it modifies, but it will take some time to go in a blocked state. Instead, the blocking transition to the zonal flow can be very rapid.
This is true.
And that's the problem with the predictability. In this sense, you have a lot of options. These guys can be transformed in this, or go back to this. And at each moment, there's these options,
Okay.
and this is a measure of the option basically that you have.
And Joachim, keep in mind that these persistences in phase space are very, very sensitive. So the most persistent states are 0.4, which would be just over 2 days,
Okay.
2.5 days. So you can't compare them to the persistence of a weather regime, which for blocking can be a week, even more.
It's not the weather regime, but it's a local measure. But it's about the options that the system have when it's there. Okay?
So the stronger theta is the stronger persistence, or
The lower theta is the stronger persistence. And this is NAO minus pattern. That is not so high dimensional, that it's quite also interesting. It's middle dimensional. Then you have seasonal dependence in this graph.
Yeah, I was going to say, yes, what's the, so like if you colour by the seasonal cycle where,
We did it, I don't have it here because otherwise the presentation would have lasted forever. But I can tell you basically that winter it's covering up most of the attractors, so you have situation anywhere, and summer is inside on the bulk of the statistics because the variation of the fields are less stronger. Of course, if you do for another variable, temperature, you will see that the extremes are mostly summer and winter, and spring and autumn are in between. Okay? Yeah?
So your plot also showed the color here for
Ah,
NO.
this is the NAO. There is also slight
So
dependence on the NAO.
So when I look at the color, I see that I have a small value of NAO everywhere.
Yeah,
Large
so the
value
NAO, the conclusion is that the NAO is one-dimensional almost. So there is some indications that statistically you have more points red here,
Yeah.
but and more blue points here, but that there is more information in the atmospheric dynamics than just the NAO index. So it was kind of a
Then if you go
warning to the NAO.
So when you say that you plot these four patterns and you say that here it's NO plus.
But this is a traditional way to look at the way this pattern has been called by the group.
Why? But my question is, if you look for NAO plus,
Yeah.
will you find some of them everywhere?
Yeah, you have also here some NAO plus.
Well, but almost by definition, because the weather regimes you assign every day to a regime, right? Here we are only considering the top and bottom 5 percentiles. So it's clear that not all the regimes will fall into the...
NAO is just a one-dimensional measure of the guys that are here and here. So an anomaly, if you can have a very local anomaly here and here, even with a blocking phase, you can just get an NAO plus. They don't have to correspond to the NAO pattern. So the NAO plus pattern is not the NAO index. It's just a traditional way to call it.
So I didn't get the idea why you put NAO plus to the left and that was the correct.
But okay, so there is a different thing.
Right.
The NAO index is different from NAO pattern. So the pattern, because this is basically how they are named, the weather regimes are named usually. So we find some kind of match. But the NAO plus doesn't correspond even when it's a pattern necessarily to a NAO plus index.
And the index is defined as the projection onto the
Okay, here this is just the NAO index, the one-dimensional difference of pressure between Reykjavik and Lisbon.
No, but there's a very large difference between what you call NAO plus and NAO minus. I mean, they're opposite in pattern. And you're saying you average all this box and you get this pattern, but if you look at the colors of the NAO,
A one-dimensional index, it doesn't match the but it's
so it means this is the, you said this is when 2/3 match, so it's the other 1/3 that doesn't.
yeah, probably, yeah. You have 1/3 that don't match. But anyway, the pattern is not the index. Here, the color is the one-dimensional index, is just the difference of the pressure in this point and this point.
So if you would do the same scatter plot for the Lorentz model,
It's very strange.
would you necessarily get that, what you're implying is that all points that D and theta characterize the
No, I'm
extremes,
not
but if
implying
you go back
this.
to, by averaging these whole
Yeah.
boxes, but if you go back to the Lorentz model, can't you have 2 points that are very, very distant that have similar D and similar theta?
Yeah, it will be the 1/3, but maybe again. But you will recognize that this region is the unstable, the unstable fixed point. So you will have the 2 unstable fixed points at the center of the wings in some region here. Then you will have the other one that has high dimension, but low persists, low theta somewhere else. And then you will have the normal part of the tractor, and the wings will be mixed up with the part in the center where you develop.
So to give an alternative answer to your question, there's no mathematical reason for which this should be. For the North Atlantic, this works very well. If you, for example, take the whole northern hemisphere, the extremes don't have any sign agreement in the anomalies. So if you want, it's a bit by chance in inverted commas that works so well.
Exactly. So here it's somehow surprisingly that we get the patterns out of the analysis of the extremes. But there is no pretension that it's going to be like this.
This is the statement I would like to understand. How do you get the pattern out of the study of the extremes?
But it's just averaging these guys.
The flow on the base point lies in.
There's a particular pattern that favors having low dimension, which is the NAO plus pattern. third of them are kind of like constant.
So that's why we are doing the study with
Well, I mean,
Neely.
actually, less than a third, because those lines,
this
black
will
lines,
work.
are more
I
like
think this
10%.
will work for it.
Yeah, but the model we have different regimes already.
Right.
So there is a regime that is more zonal, a regime that is more wavy. So we can see if when the regime is still the same through all the run, we get difference in the dimension. So there is more than just.
So you predicted 940, that was an under prediction. But since
Yeah.
since we're talking, so you talk about instability. So as an atmospheric scientist, when you think instability, you think barotratic instability, and you always think of NAO plus as being an unstable situation.
Right.
You're saying it's the least stable
Yeah.
situation. So that's a bit interesting, but so I guess what this dimension captures is the fact that the large scales can change quickly, right? Because that gives you a big divergence in the distance, right?
Yeah.
But in an NAO plus, you will get cyclones, right? I mean, they're unstable in the sense they produce
Yeah, they produce
cyclones, right?
Yeah.
So on any given NAO day, I mean, there you're averaging, but on any given NAO day, you'll have a cyclone here, a cyclone there, but a large scale. So I guess what you're capturing when you put a large scale.
Yeah. Yeah. It's definitely
right.
the large
So
scale.
the-
Yeah.
It's based
So
on the XLP.
the
so it's
synoptic
large
scale, yeah, but I mean, when you have a synoptic scale system, it's going to give you, it's quite different to have it over North America or over Europe. So, but I guess the metric, so maybe there's some sensitivity in the metric there.
To the observable.
Yeah, I mean,
Yeah.
you
Of
have a
course.
metric that focuses more on synoptic scale, so you.
I think you have to change the maybe you have to get, if you want to look more at the growing with stability during cycle, maybe you should use potential vorticity or something that is more on the quantity, cyclone related quantity. Also because these are daily maps, you know, so.
But in any case, I mean, you can see in the plot that the NAO plus is a diagonal band in the upper half of that kind of oval, and the NAO minus in the bottom half. So typically, for any given local dimension, the NAO plus is less stable than the NAO minus, which fits with the idea that it's stormy for NAO.
Okay,
plus.
so in fact, what I will show now that is not this is this. So another thing that we did is to look at the European windstorm as taken from the Wikipedia database, and then look if they fall somehow on the minima, and there is actually a very large probability to find all these guys in the minima with respect to a random test that can be anywhere on this diagram. So actually the minima corresponds to these guys there.
And what happens during NAO plus? No?
Plus plus. It's NAO plus plus.
Can you explain better what you have done?
So each day, so in this page Wikipedia there are the days where these storms occur, and then I compute the probability that these storms are in the minima with respect to the probability that they are everywhere on the diagram. So this probability is you will have 1% versus 20%. That is what we find. So the 20% are there, while we expect to have only 1% if we just look at the everything will be random. So we find that they are related to the minimum of the dimension. And the very last thing is that when I want to see. So this is for all the models CIMI 5 and all the 56 members of the 20CR. So this is a caveat for using this guy somehow. You see that the members are all here, and the 20CR is here, and the models for some reason lie in between the 20CR ensemble mean and the 20CR members. So the ellipse, these are just the median values of the dimension, okay? And the persistence. The good news is that most of the models are inside the one standard deviation of the median, in this case, for the 20CR and the 20CR ensemble mean. Yeah, the bad news is this guy is doing very strange things if we look, for example, at the temporal evolution of the dimension. But the good news also is that if we look at the dimension average over 30 years in time, and we start from a date that is not so problematic, so 1975 up to 2000, and we look at the ensemble mean, the 20 CR members, that are the light colors, the average of the 20 CR members, and the multimodal means. We see that there is some kind of trend in decreasing the dimension that will be going to a more predictable atmospheric states that will correspond, for what we say, to have a more zonal flow, because we say that what is unpredictable is the wavy part of the flow. Okay.
So does it increase then after the 2000s?
No, it keeps decreasing.
The 2000s are more, because this period corresponds to a trend toward 50 million.
Yeah.
So, and then between 2000 and 2010, there is less positive news, so I would expect.
Here you have some kind of fluctuations, but so we go to 2015 in the analysis, but here it comes there. But I remember it was going down.
Those are 30-year averages.
Moving average of 30 years, so you will probably need to do 10 years to see.
This is for the Atlantic sector.
Yeah, this is the North Atlantic sector.
Also looks like the inverse time series of the number of satellite information 1 and 2.
What?
It looks like the inverse time series of the amount of satellite information.
So, but the problem is that when you incorporate observation, more observation, and this is for the first part of the period, this guy, the red line, grows. So, giving more observation, it seems that it goes in the opposite direction of this decrease that we observe. We did a scatter plot between the variance of the ensemble, that basically corresponds to what you're saying, and the dimension of the 20 CR ensemble mean, and you see that there is a very straight line up to 1975, and then that's why I'm showing only the last part, because I think that these results are somehow independent of the
Why is there any seasonality in that curve? What?
Sorry?
I don't see any seasonality in that curve. Do you think?
because it's 30 years moving average,
Oh, I see.
so everything is
Where's the answer for?
huh?
Answer pre-analysis. Do that one?
Yeah.
Which one?
But there will be somewhere here
It also shows this.
decrease. Then other analysis show increase. The ECMWF analysis show increase. We think we can explain this, but we have to. We don't want to spoiler too much the results. So you maybe invite me or Gabriele or Pascal to the next workshop to listen and do this stuff. Okay, so it's good news if the atmospheric become more predictable.
Although
Increasing waviness.
Although
predictable.
predictability,
Should I answer this question or I don't know?
I think
Because we start.
perhaps we can take this as the one question to the speaker and then move on.
Okay.
Sorry, I also have to. You had a point there about the winter 13 and 14. Can you just very quickly say something about that?
Okay, yeah. So it was just. So this was just, and then I answer maybe ready because it takes time. So here we did.
Okay.
We just show what happens, but it's interesting because there are several storms
Yeah.
coming in. So you will see that the storms actually correspond to being in the region of the phase space. Sorry, not of the diagram. That is NO plus. So this is we are in October. So then the storms will come and we will be in this region. So here you see when there is it goes a bit fast, but when there is this ridge pattern, in fact, is there. But it's the way we got convinced also visually that it's not just
Because the intense period starts at the end of December.
yeah. Here there are Dirk, Eric, and
But the period where the jet was more or less stuck in the same place was from late December until beginning
so
of
this
March.
is late December.
Yeah, okay.
You see,
Okay.
we were there. And now then there is some kind of blocking events and we go on. And then another storm.
So maybe we can really speak about this later on or another opportunity because this would be interesting.
Okay. So the last question is how we assess predictability, and then I go away. So this is we look at this GER reforecast, so still American products, for the last 20 years, and we look at if there is some kind of relationship between the theta, for example. So the more stable, the more predictable, so the lower the error, and the higher the theta, the higher the error. But the problem is, okay, this is the error at the end of the forecast, okay, but it's the same if I show you 96 hours or 48 hours. So the problem is that this reforecast tends to have the error cluster either in very low error, relatively low, or relatively high, with almost nothing in between. So we would like that there is some kind of relationship. We know that there should be a relationship from the dynamical system theory, because the dimension is a measure of the unstable direction, and I think we will study this problem with Gabriele next. So thank you very much for the interest and also for the question. If you want to see what happens in the last days, you can go on my webpage because I run it every day. So the 2 October was more like towards an Atlantic Ridge pattern. Here you see the full attractor in the lower, very light gray points, and this is the month of October. You see, it's just a part of the attractor. Okay, so thank you very much.